Hello, I'm going to give you the inside scoop about analytics. Analytics is not magic, it's math. But I'll do the math for you today, so no worries. What you'll see is that the analytics process involves some tasks that will be very familiar to you, and some others that will seem quite strange, but it's all good. The analytics process falls under the field of data science, which can be broadly divided into these three stages. For simplicity, you can think of this as data is fed into models to produce insights. These are the major tasks that are performed during each stage, and I'll spend some time on those that may be less obvious to IT folks. Data pipelines ingest data of any structure into our platforms in batches and in streams. Exploratory analytics helps us as we transform data into features, and feature engineering usually consumes the majority of a project's time, so we'll dive in there. Features are the values that a mathematical model uses to predict a target value. Here we have many raw values which describe homes, and we want to engineer them into features that a model can use to predict each home's price. Not all raw data will become features because only an optimal set of features will produce the most accurate predictions. So let's take a look at a few of the many techniques used during feature engineering. The simplest kind of engineering happens when you use your domain knowledge to remove data that is not very predictive. The number of fireplaces and ceiling fans may be interesting to a home buyer, but they do not help predict a home's price, so including them would only complicate our statistical model. Therefore, some raw values are simply dropped and don't become features. Mathematical formulas relate numeric quantities to each other, but some raw values are not numeric. So what should we do with a categorical value like home type? It is the kind of value that can help improve a prediction, but we need to transform it first. Your instinct may be to simply assign a number to each unique home type. But then, most mathematical algorithms would assume that home type 2 is twice as important as home type 1, and type 3 is 3 times more important than type 1. Instead, we use a technique to create a new feature for each unique home type value. And then, for each home, we set each feature's value to either a 0 or a 1, depending on if the home is that type. Here's an example of how exploratory analytics can uncover the need to engineer features. This graph shows how two values are correlated, and it contains hundreds of data points, but most of them are clumped together near the intersection of the axes. Now let's look at the same graph, with both axes scaled by orders of magnitude, using the base 10 log of each value. To deal with the adverse effects of skewed data, we sometimes use mathematical methods to make a distribution more Gaussian because many algorithms assume that our features are normally distributed. This may be your first hint that data science requires a good math background. In fact, if we look back at the stages, I would estimate the mix of skills required for each like this. The majority of the skills needed for data engineering are IT related, but there is also a need for business domain knowledge and some mathematics. Speaking of math, you may see this as a row with columns, but a data scientist sees an n-dimensional vector because predictive algorithms use a lot of linear algebra under the covers. When you're dealing with hundreds or thousands of dimensions, you really need to reduce your feature set. There are many model-based techniques that we can use to reduce the number of dimensions, like these examples. One of the more popular is principal component analysis, which can replace dependent features with a few new features that adequately summarize information contained within the original feature space. This is an advanced topic, so I mention it here only to make the point that feature engineering tasks can include the use of mathematical models. This exploratory visualization shows that 90% of the variance within our data can be explained by the first four principal components, so we'll just use the first four to avoid overfitting our model. Next, I'll briefly explain what goes on in the advanced analytics stage. For a supervised machine learning task, our training set contains historic data with values for the features and a label for the target. It can contain millions of records, and they are input into an algorithm. There are thousands of different algorithms to choose from, and here are a few samples. You can tell by some of their names that there's a lot of math involved. Many use techniques like gradient descent, which learns by using calculus derivatives to find local minima. So a data scientist won't use just one algorithm. They'll actually try many different algorithms to find the one that produces the most accurate model. Most algorithms have a set of hyperparameters which must be tuned to find the combination which will produce the best model. So each algorithm will actually produce many models. Now we need to use a different historic data set to test the accuracy of each of our many models. The testing set is input into each model, and we compare its predictions against the actual historic targets, yielding performance metrics which can be used to compare all of the models to each other so that we can select the best model to productionize. We'll shift our focus to analytics engineering, which handles the DevOps details. Now that we've selected the best model, we expose it as an API, and when a new observation is passed to the API, the model returns a predicted value. We run the model and API in a virtual object, like a Spark JVM or a Docker container. For example, a model created with Python can run inside a Docker container that includes Linux, the Python interpreter, our fitted model, the Python packages used to create our model, like TensorFlow, Keras, SciPy, and NumPy, and a Python web framework, like Flask or Django. And then you probably know the rest of the story. Our container runs inside an orchestration object, like a Kubernetes pod, which runs on a server node. And we can make our machine learning model scalable by running it across many nodes. The last thing I'll mention is that in addition to typical IT monitoring, we also need to watch the performance of our model to see when its accuracy starts to degrade, signaling that it's time to retrain the model with fresher historic data.